And we are back to practice some more exponents. This is a fun one that my math mentor taught me this year. It is a fun way to practice with students of pre-algebra level all the way to pre-calculus. It is also fun because it's a way that I've never seen in any textbook. Shout out to FJW if you're watching this. All right, so the main idea is that we're given this key, these three pieces of information, and we want to evaluate these exponential puzzles, meaning evaluate, do give them a numerical value. So let's see, let's start to think together and maybe you can figure some of these out on your own. Let's think about what's happening with exponents here. What's happening is that exponents are being added. What's happening with the exponents here? Subtracting. Happening here, adding exponents and subtracting exponents. Something should be coming to mind. When do we add exponents based on our rule of exponents? For what situation does that occur? When we have multiplication. So here we should see expect to see something times something, some type of product, right, with the same base. Think about this one. What is going on right here? Subtracting exponents means that we should see some quotient, some division of the same base. What's going on right here? Adding means we have something times something. And then subtraction here implies that we have division. Keep that in mind. And then let's see, what is it being multiplied here? Same base is 5. The first exponent is x. So therefore 5 times 5 to the x times 5 to the second. That's the product. How can we rewrite this one here? This one is 5 to the, because of subtraction of exponents, we have 5 to the y. Same base, 5 to the first. The order does matter for this one, so be very careful. What is going on here? Adding exponents means we have something times something. What's the first thing? It is 5 to the x times 5 to the y. And then same type of thinking here. We have 5 to the, is it 5 to the x over y or 5 to the y over 5 to the x? It's order matters here, and it is 5 to the y over 5 to the x. I don't know if I said that correctly, but that's what I was thinking. And then this is where we would stop on a particular practice from before, but we have more pieces of information here. Look, we have something times something that we can now make a substitution for 5 to the x. What is 5 to the x the same as? It is a 2. 5 squared we can evaluate. That's 5 squared is 25. So it turns out that this expression simplifies to 50. 2 times 25 is 50. So 5 to the x plus 2 is 50. That's what we're evaluating here. That's the puzzle we're trying to solve. What is that exponential? Looks like a weird 0. All right, what does this expression simplify to? Can we simplify further? 5 to the first is just 5. And we know that 5 to the y is 3. 5 to the y is 3. Therefore, this expression is 3/5. That's pretty cool. That wasn't very clear at first, but now that we rewrote it, it's like, oh yeah, it's 3/5. It's very easy to see. This one right here is 5 to the z times 5 to the, oh, that was a mistake. I wrote x. Let's read. I'm glad you guys caught that too. 5 to the z times 5 to the y. That's what's going on right here. And we can make those substitutions. 5 to the z is 7. So we have 7 times some other number, 5 to the y. 5 to the y is 3. So therefore, this expression becomes 21. That's pretty nice. And this right here is 5 to the y minus x. Did we write it in the correct order? Yes, we did. And let's make some substitutions. What is 5 to the y? 5 to the y is the same as 3. And 5 to the x is 2. So be careful. It almost looked like 3/5 again, right? But it's not. It's 3 over 2. There we go. We're able to evaluate the first 4 exponential expressions. I'll give you some time if you want to try the next few. And here's the key below. The same numbers, is just easier for us to see down here. All right, if you tried it already, we can check the work now. So remember, we're looking for our rules of exponents. What's happening in the exponent? Multiplication. So what should we expect to see down here? We should see a power to a power. What do we have in the exponent here? We have addition. So what should we expect to see down here? We should see a product. Here in this exponent, oh, there's more than one thing that I noticed. There's a product for sure, and there's a negative exponent. So not only should we see a power to a power or exponent to exponent, we're also going to see reciprocal. All right, so keep thinking reciprocal. And what's happening here? Subtraction implies we should see a quotient. Let's go through the motions. So Power to a power because we see product, and there's two ways we can write it. We can either write this as 5 to the 4th to the y, or we can write it as 5 to the y to the 4th power. Based on the information given, which one is going to be more convenient here? That's a y, but not a 4. So they both look like y's. It's kind of weird there. All right, which one's more convenient here? We can evaluate 5 to the 4th, which is 625, but there's nothing about it down here. But look, we do know something about 5 to the y, so we're going to go with that one. This one right here is 5 to the y is 3, and then raised to the 4th power. So this is 5 to the y to the 4th power, that's 81. So 81 is the same as 625 to the y, but that wasn't part of the puzzle, but it's just, given those conditions, those are the same, but what we wanted is 81. I just thought it was pretty cool to show that 625 to the y is the same as 81. All right, next one is addition implies that we have a product. What's being multiplied? 5 to the x times 5 to the y. And that becomes something times something. That's already in the chart. 5 to the x is 2. 5 to the y is 3. Therefore, this becomes 6. That was pretty easy. Very similar to the things we did above already, like these. All right, this one's kind of cool. I wonder how you guys thought about it. Maybe I'll show a little bit more work than I would like to, but just to show the thought process. Because I see a product, and again, I kind of see what was going on here. There's two ways of writing it, but I think the more convenient way to write it is going to be 5 to the x to the negative 3rd power. Those are the same. Verify that for yourself. Product is the same as that. The order doesn't matter in which you write it. And 5 to the reason for doing that is 5 to the x is 2. So now we can say 2 to the negative 3rd. And then we know that that is simply the same as 1 over 2 to the 3rd. However you want to think about that, all right? But that becomes 1 over 8. That one's pretty cool. Told you we would see a reciprocal there at some point. Nice. So what should we expect to see here? A quotient. We have in what order? 5 to the something over 5 to the something. What's the order? Is it z on the numerator or is it x? It's x because the first thing that was written there, that was not too bad. Nothing, no trickery there. 5 to the x is 2. And 5 to the z is 7. So this expression is 2 over 7. All right. Let's see what else could be other options in these puzzles. Ooh, okay. Starting to look a little more intimidating, but not really. Just because you see a fraction doesn't mean we change the way we think about it. But a little reminder, for even from previous videos, a little reminder, if we see something like y over 2, this is just for your reference, that's the same as 1 over 2 times y. Or in this case, if we see z over 3, I'm going to think of it as 1 over 3 times z, all right? I'm going to use that idea throughout here. So keep that in mind. There's a little reminder, not that that's part of the problem, but you do need to be comfortable with that idea, so that this one, we do think of it that way, is 5 to the 1/2 times y. And now we think, which option is better? There's nothing about square root of 5 on the table, so I'm not even going to rewrite it in that format. I'm going to go straight to 5 to the y times, or to the 1/2 power. Instead of 5 to the 1/2 power inside the parentheses and then to the y, that wouldn't take us anywhere. So then we know that 5 to the y is 3. So this is the same as 3 to the 1/2. And when we see a power of 1/2, what should we expect to see? We should expect to see a radical. I forgot to ask that question, but keep that in mind. So this is radical 3. That's pretty cool. And if the 1/2 power implies we should expect to see a radical, what does the 1/3 power should give us as a hint to anticipate for as a result? It's got to be some form of a radical as well, right? And if you notice the cube root, if not, let's show it. This is the same as 5 to the 1/3 times z. Whoops, let's redo that. Oh, that's bad z. Okay, that's better. We're just going to keep that as 1z. And then that's the same as 5 to the z to the 1/3. And what's 5 to the z? It is a 7. So 7 to the 1/3. How do we rewrite that with radical form? The 7's inside, and the root is 3. The root is 3, so it's on the outside of the radical. And the 1 is implied, so I just won't write it, but it is invisible there as 7 to the first. That's the way I'm going to write this radical. That's pretty cool, right? That's awesome. Then we see another exponent. That's a fraction here. So again, we should anticipate some form of a radical. Let's see what that is. This one becomes 5 to the x, because we see a product of, think of it as a product of 4/3 times x. So all of that to the 4/3. And 5 to the x is 2. 2 to the 4/3. Again, we should be comfortable writing these radicals as 2 to the, what's inside or what's the exponent for the 2? Is there a 4 or a 3? It's definitely the 4 because the root is 3. So that's the cube root of 2 to the 4th. It's the way we can write it. Cube root of 16 if you prefer, but I like to see the base 2 on the answer. All right, those are pretty nice radical examples. We had examples where we were subtracting exponents, multiplying them. Let's see what else. Oh, now we're starting combining these ideas, it looks like. And see if you want to try those ahead of my pace. Otherwise, let's check it together now. And again, same idea from before. Think of it as 5 to the 1/2. And maybe I'll show this working in each step times x plus 3 in parentheses like that. This is probably the way that I would write it. And then again, because this is a product, it means we can change the order of the power to power. I'm going to write as 5 to the x plus 3. That to the 1/2, like this. Hopefully you're following along. That's the same. Verify that for yourself. 1/2 times this whole thing becomes that. And then we can work with what's inside. We see addition of exponents, and we see this 1/2. So we should see a power, some kind of a product, and we should also expect a square root at some point. So therefore, this becomes 5 to the x times 5 to the 3rd. Verify that for yourself to the 1/2. And now that's useful because we do know something about 5 to the x. It is 2, and we can figure out what 5 to the 3rd is. Let's make those substitutions. 5 to the x is 2 times 5 to the 3rd is 125. To the 1/2 power means we take the square root of what's inside. That's pretty nice. That's 250. I'm running out of space here, so I'll just write the answer above. That's the same thing as the square root. Square root of 250. That's the same as 250 to the 1/2. That's pretty cool. I like that one. Like we said, we should expect some product and square root. All right, so what comes to mind when you see something like this? We see subtraction and we see a 1/3, so cube root and some kind of a quotient. Let's figure out what that will look like. How would we break this apart first? We would say 5 to the 1/3 times c minus 4. When I say break apart, I mean like factor out. And then that allows us to say, all right, we have a power to a power. Let's use the first power of z minus 4. And that to the 1/3. Those are the same. This is the same. This expression is the same as that one. Maybe I'll do it like this. This is the logic we're following. All right. And then what happens when we're subtracting exponents? We can rewrite that as 5 to the z over 5 to the 4th. All of that to which power? To the 1/3. And then we can make some simple substitutions based on our table now. Or just one substitution. It looks like it's 5 to the z. This one right here, that's 5 to the z. That's the same as 7. So 7 over, what's 5 to the 4th? Did we do that before? No, we did 5 to the 3rd. So then this one must be 625. You check it for yourself. 625 to the 1/3. But let's not leave it in this format, even though it's correct. Remember, this means the cube root. So take cube root of the entire thing in parentheses. So write it as the taller version of the cube root and say this is 7 over 625. That's pretty cool. That one evaluated to this, and now we're seeing those more intense radicals in action. It's a little more complex. All right, one more. That involves a 1/2. You see that? Now there's subtraction. It's not the same type, but something similar. Right? Think of it as this exponent minus that exponent. Oh, that's quite nice. So then we can think subtraction, and we should see square root at some point. So therefore, we will rewrite this as 5 to the y over 2. That's the entire exponent over 5 to the x. And remember that that becomes 5 to the y raised to what power? To the 1/2. I've written it many times, so I hope that you feel confident with doing that yourself at this point. And over 5 to the x. What's 5 to the x? That's a 2 on the denominator. And on the numerator, we have something to the 1/2. What's the something? 5 to the y. It's 3. Oh, one of my favorite numbers in all of math is square root of 3 over 2. I wonder if I did that on purpose. Maybe. Square root of 3 over 2. Nice. All right. See if you want to try these last two for yourself. If at this point you caught most of the idea up to this point and you want to leave, that's up to you. You can check the work later at another time. Let's do it now. All right, so now we see more things going on. Addition of exponents and subtraction. So we should visualize a product and a quotient. Here we have something over 3, so a cube root, and then minus some addition. There's a lot going on there in the exponent, so I probably think product. But let's write it out. I would write it as, okay, I see, to minimize my work, I'm probably going to think of it, the subtraction jumps out at me the first. That's the one that I want to be the most careful with. So that's why I'm going to think of it as this whole exponent minus this exponent, minus just that exponent. So therefore we can say, all right, that's subtraction of 5 to the, of exponents y plus c, division of this over 5 to the x. And that's kind of nice because now in the numerator, we can rewrite it as 5 to the y because the exponents are being added times 5 to the z over 5 to the x. And what does that become? We can start making some substitutions. We have 5 to the y is a 3, and 5 to the c is 7. 5 to the x is 2, so 21 over 2. I'm done. All right, hopefully you got the same answer. And then this same idea applies here. Because I see the subtraction, I'm going to think of this exponent minus that exponent. That's kind of nice again because we can write the quotient 5 to the z over 3 over 5 to the x plus 1. Let's simplify those separately, but using our skills that we've acquired at this point. This one will be the numerator 5 to the z to the 1/3. That's definitely what's going to work there. And down here, it's not bad. 5 to the x times 5 to the 1st. You should recognize that. 5 to the z is a 7. So 7 to the 1/3. Oh, I didn't want to write that, but it's okay. And then 5 to the x is a 2 times 5 to the 1st. That's just 5. So here we will get a cube root of 7 over 10. So I hope that's correct. Yep, that should work. Cube root of 7 over 3. And we should have matching answers. I wanted to say one more thing. If you want to write your own problems, look how easy it is to write your own problems. In this case, just change it to a different base and choose different numbers and explore what else can be written out here. I was going to write a few for you to try, but then I felt bad if I didn't go over them. But this is the end of the practice up to this point. I hope that you had as much fun as I did solving these puzzles. And I hope that you come back and hear me talk about some more math problems in the next few videos, all right? So have a good day and thank you for your time.